Earlier in the course, in the joint distribution section, we talked about covariance and Pearson's correlation coefficient. Now we want to revisit that idea of the correlation coefficient to talk about that and the residual, which are both key parts of regression, the focus of this section. So if you remember, Pearson's correlation coefficient, which we often indicate with this variable r, is equal to 1 over n minus 1, where n is that sample size, multiplied by the sum of these two products here, x sub I minus the mean of x, divided by the sample standard deviation of x, and then y sub I minus the mean of y, divided by sample standard deviation with respect to y. Realize here that we could also write this formula this way, because both of these values here are basically the z-scores for x and y. If we look at these here, we recognize them as the formula for a z-score. X minus the mean of x divided by its standard deviation is the z-score for x. So we can replace each of these fractions with the z-score of x, the z-score of y. So this is another way to write the correlation coefficient. And then this formula here is the one that we used earlier when we talked about the correlation coefficient and covariance. All three of these get us to the same place, so we can use whichever formula is most convenient. Remember that the value of the correlation coefficient always falls on the interval -1 to 1. So we'll never find a value for the correlation coefficient that is less than -1 or greater than +1. The correlation coefficient will always take on a value somewhere in the interval -1 to +1. And remember that the value of this correlation coefficient just tells us how strong the relationship is between these two values, x and y. So if we think about a scale for the correlation coefficient, so we could almost sketch a number line like this, where the correlation coefficient is -1 over here, +1 over here, and 0 at this point. The closer we are to -1 for the correlation coefficient, the more we say that a regression line with a negative slope perfectly describes the data. So if the correlation coefficient is exactly -1, it means that all of the points in the scatter plot, all the points in the data set, lie along the regression line exactly. They all lie directly on the line. None of the points are away from the line. So for instance, if we say that this is the regression line, maybe it looks something like this, then all of the points in the scatter plot lie directly on this line. There are no points away from the line at all. Whereas if the correlation coefficient is equal to +1, that means that a regression line with a positive slope perfectly describes the relationship in the data, perfectly describes the position of all the points in the scatter plot. So that means that all of the points in our scatter plot lie exactly on this regression line. If the correlation coefficient is exactly 0, that means that a line doesn't do a good job at all of describing the relationship in the data, which means our scatter plot might look something like this, kind of like a blob. There's no obvious linear relationship here at all. We can't really identify any line that starts to describe some kind of trend in this scatter plot. And if we lie somewhere in between, so if r is between 0 and -1, that means that our regression line has a negative slope, so it might look something like this, but that it doesn't perfectly describe the data. So we might have some points along the line, but we'll also have some points away from the line like this, but we see this general negative trend. And then of course that means that a correlation coefficient between 0 and +1, so somewhere over here, means that the regression line is going to have a positive slope, so maybe something like that, but that the data will not lie all along the line, so we might have some points on the line, but we'll also have some points away from the line like this. Don't confuse the value of the correlation coefficient r with the slope of the regression line. So imagine here all of these regression lines, this regression line, this one we already sketched, and this one right here. If we had scatter plots for each of these regression lines, where all the points in the scatter plot lie perfectly along the regression line, then each of these scatter plots would have a correlation coefficient of 1, but you can see that the slope of the regression line is different for each plot. In other words, a correlation coefficient between 0 and 1 just means that the regression line has a positive slope, and a correlation coefficient between 0 and -1 means that the regression line has a negative slope, but the value of the correlation coefficient doesn't actually tell us the slope of the regression line. All it tells us is that the closer we are to +1, the more tightly clustered the points are around a regression line with a positive slope, and the closer the correlation coefficient is to -1, the more tightly clustered the points in the scatter plot are along a regression line with a negative slope. Now, remember that to calculate the correlation coefficient, we can use any of these formulas here. If we use this third one, we can create a small chart to quickly make this calculation for us, and here's what that chart should look like. So if we have raw data given by these columns, X and Y, so these are the columns with our raw data. The values of X are 0, 2, 4, 6, 8, 10, and 12. And the values of Y that correspond to each of those X values are given in this column here. In other words, we have coordinate points here, X, Y. So one coordinate point in the scatter plot is 0, 0.8. Another coordinate point is 2, 1. Another coordinate point is 4, 0.2, etc. So we have all these coordinate points. You can see that there are 7 data points. And so if we're using this formula to find the correlation coefficient, you can see here that we're going to need the mean of X and the mean of Y, which means that we sum all the values of X, we get 42, and then we divide by the number of data points we have, which is 7. We have 7 data points here. So we divide 42 by 7 and we get a mean of 6. We sum all the values for Y, divide by 7, and we get a mean of 0.8. So that means that the mean of X here is 6, the mean of Y is 0.8. So we have those two values. And then for each value of X, we need to find X sub I minus the mean. And for each value of Y, we need to find Y sub I minus the mean. So these next two columns here, to get this -6, we take this particular value of X, 0, and we subtract the mean. So 0 minus 6. To get -4, we take 2 minus 6. To get -2, we take 4 minus 6, etc. So to find each of these values here, we subtract the corresponding mean from each data point, and we get these two columns. Now our formula tells us that we have to multiply each of those values together. So each X value multiplied by each Y value. So -6 times 0 gives us 6. -4 times 0.2 gives us -0.8. So we find that product. In other words, when we multiply these two together, we get this product here. And then summing all of those products, so to find this sum, or the entire numerator here, we take the sum of all of these products and we see that sum right there. So 1.6 is the value of our numerator. And then in the denominator, we again have these X sub I minus the mean of X values, but we need to square them. So we use this column here to square all the values in this column. In other words, we are getting this squared value here in this column, and we're getting this squared value here in this column, and then we need those sums. So to get this sum here, and then separately this sum here, we need to add all the values in each column. So we get that sum and that sum, and then taking the square root of the product of those two is the same as taking the square root of each of them individually and then multiplying them together. So we can take the square root of both of these values. So we get those square roots here and here. And if we multiply these together, we get the denominator. So this entire denominator here is the product of these two values here. So if we multiply these two together and then we take 1.6 divided by the product of these two, we get the correlation coefficient R. And so the correlation coefficient for this data set here of X and Y values, this raw data, our correlation coefficient is 0.101. So the fact that this value is positive tells us that the regression line through this scatter plot is going to have a positive slope. But the fact that this value is very close to 0 instead of +1, so the value is maybe right about here, means that the correlation is very weak. We don't have a strong correlation like we do over here where all the points in the scatter plot lie exactly on the regression line. Instead, the points are very spread out away from the regression line, but the regression line does have a positive slope. So if we replace this table with a scatter plot of the raw data, then we can see the relationship we were talking about. Here's the regression line through the scatter plot of that raw data that we were just looking at. We can see that the regression line does have a positive slope because as we move to the right, the line moves up. So we've got a positive slope, but the data is very spread out away from the regression line. It's not tightly packed or tightly clustered close to the regression line. So it does make sense that we would find a correlation coefficient that is very close to 0, but still positive to indicate the positive slope of the regression line. That being said, as a general rule of thumb, we do classify the strength of the correlation based on the value of this correlation coefficient. So in particular, if the correlation coefficient is specifically between -1 and -0.07, we tend to call that a strong negative correlation. Whereas if we're kind of in that mid-negative range between -0.7 and -0.3, we would call that a moderate negative correlation. And then if the correlation coefficient is between -0.3 and 0, we would call that a weak negative correlation. And then we have the mirror image of those relationships on the positive side. So between 0 and 0.3, we have a weak positive correlation. Between 0.3 and 0.7, a moderate positive correlation. And between 0.7 and 1, a strong positive correlation. So our correlation coefficient of 0.101 would fall within this range right here. And so we would say that this data has a weak positive correlation. Now, related to the correlation coefficient, at this point, we need to talk about the residual as well. So the residual for any data point, in other words, every data point has a residual. The residual for any data point in a scatter plot is the difference between the actual value, so the data point itself, and what the regression line predicts at that same value of the independent variable. So if we say here in this scatter plot that this is the horizontal x-axis, this is the vertical y-axis here, we could look at, as an example, this data point here. Its actual value is 2, but its predicted value is what we find along the regression line if we follow this data point down to its corresponding point along the regression line. So it looks like the predicted value, so this is the actual value, and then this value right here is the predicted value. It looks like this predicted value is maybe about 0.85, something like that, roughly. So the residual is the difference between that actual value and the predicted value. We can write it this way. The residual is actual minus predicted. Or mathematically, we would write that this way because we often also think about the residual as error. And so we represent the residual with the variable e. And then the actual value here is the actual y value of the data point. Remember, this data point here is a coordinate point x, y. And so it has its actual y value, but then the corresponding y value along the regression line, remember that we write the regression line or the equation of the regression line as for y hat. The equation of the regression line is y hat equals mx plus b, where m is the slope of the regression line and b is the y-intercept. So the predicted value along the regression line is always given by y hat. So if we look at the residuals for all the points in our scatter plot, we would show them like this. These are all the residuals. It's this difference. We could also think about it as distance, the distance between each point and the regression line. So the points that are closer to the regression line will have a smaller residual. The points that are further from the regression line will have a larger residual. If the point in the scatter plot is below the regression line, its residual will be negative. So everything down here, all 4 of these points here, will have a negative residual, whereas these 3 points up here will have a positive residual because of their position in relation to the regression line. And now that we understand this idea of the residual, we can define the regression line in a new way. What we can say is that for any regression line, any y hat equation representing a regression line, we know that the sum of all the residuals is equal to 0. That is another way to define or identify the regression line. The regression line will always be the line that makes the sum of all of these distances equal to 0. That also means that the mean of the residuals is equal to 0. And in general, that should make sense because the idea of the regression line very, very broadly is that it's trying to balance out all of the data points in the scatter plot. And if we're creating balance in the scatter plot, we can think about that as trying to balance all of these residual values, the distance of each point to the regression line. And so the mean of the residuals is going to be 0. The sum of the residuals is going to be 0. Now, we've already looked at in the past how to calculate the equation of the regression line. The equation of this regression line in particular is y hat equal to 0.0143x plus 0.7143. Both of these values for m and b are rounded to 4 decimal places. But this is the regression line equation. And so what we can do once we have the regression line equation is create a table of actual and predicted values, and then use those to calculate the residual for each data point. So we can create a chart. These first 2 columns are all of the raw data that we looked at earlier. These are all of the x values, and then these are all of the y values, or the actual values for our equation here. The predicted values are the values we get from our y hat equation, our regression line equation. What we do is we take each value of x and we plug it into the y hat equation. So you can see here, if we plug in x equals 0, then this term goes away and we're left with y hat is equal to 0.7143, and we see that here, 0.7143. So we're getting these predicted values out of the y hat equation, and then we know that the residual we can calculate as y minus y hat, and so we find the value of the residual, we find the value of the area. And we see here, in fact, these 3 positive values that represent the 3 points above the regression line, and the 4 negative values that represent the 4 points below the regression line. Now, the reason that we're looking at this chart is because we can use it to illustrate these 2 facts here that we just talked about, that the sum of the residuals is 0 and that the mean of the residuals is 0. Because if we create a new scatter plot where we have our x values along the horizontal axis, just like up here, but now along the vertical axis, we plot the value of the residual. So notice here that in our vertical axis, the value of 0 is here in the middle. And so we have some negative values below 0 and some positive values above 0. If we plot each of these values of the residual in this new set of coordinate axes, we get this scatter plot here. Ignore the yellow line for a second. We get this scatter plot with all these new points. What we see is that they all correspond in terms of their position to the scatter plot up here. We've just changed the vertical axis. So now this point, instead of being plotted with a vertical value of 2, is being plotted with a vertical value of about 1.17. We see that point here. These 2 points down here are the negative 0.57 and the negative 0.60. In other words, up here in this scatter plot, all of these points are plotted as XY coordinate pairs. Down here in this scatter plot, all of these points are plotted as X, Y hat coordinate pairs. And when we use this new set of coordinate points, when our coordinate points are given by X and Y hat, and we use that set of coordinate points to find a new regression line equation, that new regression line equation is this line here. We'll call it Y hat of the residuals. That new regression line equation is the equation Y hat equals 0. In other words, another way to put this is that if in this plot, the points in the scatter plot are pretty well spaced out with a bunch above this y equals 0 line and a bunch below this y equals 0 line, that means that a linear model is going to do an okay job describing the trend in the original scatter plot with the original set of data. So if you remember, we said before that this regression line, this line of best fit, this line of least squares, we have a bunch of different names for this regression line, this trend line. We said before that we were always trying to minimize the sum of squares. So we would look at each data point in the scatter plot and we would think about creating a square between that point and the regression line. So we would have a square like this, and then we would have a square like this, and then this one up here would be really, really big. This square here would look something like that. Let's just go ahead and make this big one. So we have this big square. We said before that we were trying to minimize the sum of all of these square areas. Well, now that we know that the side of each square can be described as the residual E, if we just say that E sub n represents all of the residuals, and we square that value, this is all of the squared residuals, and this is the sum of all of the squared residuals. This is the value we're trying to minimize to find the very best fitting line through the data, through the scatter plot, to find the equation of the regression line, to find the equation of the trend line, the line of best fit, the line of least squares. This is the value we're trying to minimize when we describe that value in terms of this new idea we've introduced, which is the idea of the residual. Thinking about this in the context of the residual also gives us a better idea of why we look at the squares instead of just the pure distances. In other words, instead of just pure actual minus predicted, the distance from the data point to the regression line, we instead look at the squared area. And the reason is because in the context of the residual here, we get a positive residual for any points that are above the least squares line. We get a negative residual for any points that are below the least squares line. And if we have a bunch of points above and below the line, those positive and negative distances would cancel each other out if we didn't square the values to turn them into areas. So if for this point we got a residual of +1, and if for this point we got a residual of -1, those two things would cancel each other out completely, and we wouldn't necessarily be optimizing for either of those data points. When we square the residuals, we get two pieces of squared area. They both count as positive pieces of area, and so we can make sure to account for minimizing both of those areas when we're building the equation of our regression line. So we're always trying to minimize the sum of the squared residuals, or the sum of these square areas. So that process of trying to minimize the residuals by minimizing the squares of the residuals, that's where we get that name, least squares line, or line of least squares, or we often call this process least squares regression. We're just trying to minimize the total area of all of these squares.